Okay, so this time what I'd like to do is give some examples of calculating the polar form of some complex numbers. So let's start with the following example, which is we let z equal 1 plus I times the square root of 3. Okay, so the first thing to do with these is always draw a picture. Because you're going to, otherwise you might well have problems with the argument. Okay, I mean the argument of the complex number, that is. So let's draw a little picture, just so we know where this is going to be. So what we've got is 1 plus I times the square root of 3. The square root of 3 is about 1.86, something like that, if memory serves me correctly. So it's I, that's 1. So root 3 times I is probably up there. So the complex number we're after is approximately there. Okay, so then draw a straight line down to the origin. So this is our complex number z. We're trying to calculate the polar form of this complex number. So what we need is its modulus and its argument. So the modulus of z is just the length of this line here. So the modulus of z is just the length of that line. So the modulus of z is equal to, use Pythagoras' theorem, the square of the of this side plus the square root of that side, and take the square root. So that's just the square root of 1 squared plus the square root of 3 squared. So that's the square root of 1 plus 3, which is the square root of 4. In other words, 2. Okay, so the modulus is 2. So the next thing to do is calculate the argument. So the argument is that angle there. So this is the argument of z. In fact, that's the principal argument because that's between 0 and pi. So that will give us the principal argument. So what is that? So we can calculate that just by using tan. Well, you can pick. We know what that side length is 2. That side length is square root of 3. That side length is 1. So we can use tan, cos, or sine. So in this case, well, let's use. Well, we know that tan of arc z is, so b over a, so it's that over that, so it's root 3 over 1, which is root 3. So you can just check or remember that that means that the so arc z, the angle is equal to 1/3 of pi, so pi by 3. So it's 60 degrees, so it's 1/3 of the way round to the negative real axis there. Okay, so we've got the modulus and we've got the argument. So this tells us what the polar form is. So z is equal to 2 into cos pi by 3 plus I sine pi by 3. Okay, it's one way of expressing z as a complex number in polar form. Okay, so that's the first example. So that's a sort of nice easy example because we're in the first quadrant here. So calculating that angle is just a bit more, you just have to have your wits a bit more about you if you're not in the first quadrant there. So let's have a look at one which isn't in the first quadrant. So if we now take z to be equal to -1 plus I, what do we do? First thing we do, draw a picture. Okay, so we draw it on our argon plane. So we've got -1, say there, and I is there. So the number we're after is that point there. So that's our z. And we can draw the line joining it to the origin. So the modulus is just the length of that line, and the argument, the principal argument, is that angle there. Okay, so that angle is the argument of z. And the length of this line is the modulus of z. Okay. So again, to calculate the modulus of z, you can just use Pythagoras' theorem. So the modulus of z is equal to the square root of the square of the other two sides. So that's just the square of 1 squared plus 1 squared. So that's the square root of 2. And that's what it is, the square root of 2. And what's the argument? So here, well, if you just calculate tan, if we do what we did last time, so what we know is that the tan of arc z is going to be b over 8. So that'll be, the height is 1, and we go -1 in that direction, so it's -1. Now if you just type that in your calculator, what it will tell you, so your calculator will tell you that arg z is minus pi by 4. And that's wrong. So if you just work out what the inverse tan of -1 is, it will give you minus pi by 4. Because that will give you minus pi by 4 is this angle here. And that has the same tangent, so that has the same slope as that point. So the point down here has the same slope running through the origin as that point. So they have the same tangent. Okay, so we have to be a little bit cleverer. So we know that the argument here is it's greater than pi by 2 and it's less than pi. Well, there's various ways we could work that out. So we could just work out what this angle here is and take it from pi by 2, or we can work out what this angle is and add it to pi by 2. Sorry, we could have worked out what the angle was and subtracted it from pi, which is the whole thing, or we can work out that angle and add it to pi by 2 there. Okay, so this angle here, if we just call that angle phi, so I mean, as I say, there's many ways you can do this. This has the opposite is 1, so the length of that is 1, and the hypotenuse we've worked out is root 2. So sine of phi is equal to opposite over hypotenuse, so it's 1 over root 2. So that implies that phi is equal to pi by 4, so 45 degrees in other words. So this whole thing is, so arg of z is equal to 3 pi by 4. Okay, so we've gone 3/4 of the way around to the minus imaginary axis. Okay, so that tells us all together that what the polar form of z is. We know the argument and we know the modulus. So z in polar form is the square root of 2 times cos of 3 pi by 4 plus I sine 3 pi by 4. Okay, and that gives us the polar form.